Ether, as well as the people in the room, with Alberto Caimo about Bayesian ERGMs and looking at both computational and modeling challenges. Thank you.
Thank you. So, thank you for inviting me to give this seminar. So basically, my talk is going to be about Bayesian exponential random graph models, and I will emphasize some computational modeling challenges that these family of model is currently facing. So this is the outline. So first of all, I will introduce briefly the modeling framework. Then I will give some brief review of computational approaches that have been proposed recently. Then I will focus on two particular modeling issues, so network dynamics and network heterogeneity. So first of all, exponential random graph models are defined as the probability of X. So X in this case is a adjacency matrix, which is describing the connectivity structure of a network. So in this case, as in many network models, we are only interested in modeling the topological structure, the connectivity structure of a network. So the assumption is that the probability of observing a specific graph of this given structure of the graph is equal to the exponential of S of X, which is a vector of network statistics observed on the graph, times associated parameters, vector, theta, minus gamma of theta, which is an intractable normalizing constant. So generally, gamma theta is intractable because we want to explain, basically describe the connectivity structure of a network by including in the model network statistics that are capturing the local dependence of in a network. So generally these statistics are quite, can be anything basically. So from edges up to triangles, if we have an undirected network context. But we can potentially also include for cycles and other higher level network statistics. In the case of directed networks, we have, of course, directed edges, mutual edges, potentially any type of network statistic that we are interested in. So the choice of the statistics that we want to include in the model is generally driven by the application we are interested in. So for example, the transitivity structure is one of the most important features to include in the model. So generally transitive triads, cyclic triads are very important. And of course, these statistics can also be somehow described in terms of covariance information. So if we have covariance information, we may want to, for example, to understand the importance of statistics like cyclic triads within groups. So within, for example, people sharing a common covariate, and see how this describe the relative prevalence of these type of statistics in describing the entire topological structure. So these are, except for edges and mutual edges, two stars, two stars in general, stars and triads and cycles are generally extradyadic features that are generally not included in other standard network modeling frameworks. So this is the particularity of the ERGMs. The price to pay is this normalizing constant. So the normalizing constant would have to be evaluated over all possible graph configurations, and for graphs that are more than 20 node, that have more than 20 node, is basically computationally unfeasible to calculate that normalizing constant. So this is the issue. Of course, conditional interpretation, so logic of the probability that two nodes are connected, given the rest of the network fixed, is equal to theta, the parameter value, times Sijx, which is the so-called change statistics. So it's the value of the vector of statistics, supposing that the two nodes I and j are connected, given the rest of the network fixed, minus the vector of statistics, supposing that the two dyads are not connected, so xij is equal to 0, given the rest of the network fixed. So basically this represents the effect on, that a single dyad has on the model's network statistics. So the contribution of a single dyad in somehow in the effect on a given statistic. So these statistics can be anything. So it can be edges, 2 stars, 3 stars, whatever we want. This is the Bayesian framework. So we have an observed network X. We observe the network structure. We specify an ERGM model. So we choose the type of local statistics, network statistics that we want to include in our model. And then we have a doubly intractable posterior. So we have the probability of theta and m, potentially, if we want to choose between different models, given x, so given our data set. And then we want to do standard Bayesian inference, so parameter inference, probability of theta given x, and model selection to select the most likely model between among a set of competing models. Once we have selected the best model and we perform the parameter inference, we may want to compare realizations from the posterior estimate. So we simulate networks from our estimate and we compare these simulations, the simulated graphs, with the original graph in terms of degree statistics, otherwise shared pattern statistics, and this kind of stuff. So we want to compare the overall topological structure of the network simulated from our posterior density to the observed network that we argue. So as I said, the issue is that the posterior density is doubly intractable. So we don't have the likelihood, basically, because the normalizing constant cannot be computed. We don't have the marginal likelihood. We don't have the evidence. So this is a so-called double intractable problem, and naive Metropolis Hastings algorithm cannot be used in this case. As you see here, we still have the issue of computing the normalizing constant. So we need something more sophisticated than just standard MCMC algorithms. What we proposed a few years ago was to adapt, to approximate the exchange algorithm proposed by Mari et al. In 2006. So we have a sort of MCMC within an MCMC, where instead of just having a Gibbs update of theta, of the parameter, we also have a draw of auxiliary data at each step of an MCMC algorithm. This allows us to get a sort of important sampling estimate of the ratio of normalizing constants that we cannot compute, basically. So we have a draw using an MCMC, a tie-no-tie, in this case, procedure, and we have this augmented likelihood. So we have the black ratio of Q's is the standard ratio that we would have in a standard MCMC algorithm. We augment the likelihood, the posterior distribution by including also the ratio of the blue terms that are a normalized likelihood based on the auxiliary data that we have generated. This way we have two additional Z terms that allow us to simplify, to calculate basically the acceptance ratio. And this is a valid MCMC algorithm. The issue is that when we update, we cannot perform perfect sampling. So we are forced to simulate data at the step 1 II. So the draw is still an MCMC, so it's an approximate exchange algorithm for that reason. So we don't have perfect sampling available for ERGMs, and we need to simulate data. So as n, the number of iterations used for simulating our auxiliary data, sufficiently large, as n increases, the number of iterations increases, the exchange algorithm will, the approximate exchange algorithm will tend to of course, to be an exact exchange algorithm. So we have basically two types of approximation here, because we also have an MCMC procedure and another MCMC procedure within the MCMC procedure. So this is why it's an approximate exchange algorithm. In order to improve the mixing, we also adopted a few strategies. So, for example, we used adaptive direction sampling in order to sampling efficiently to move efficiently to improve the mixing and the convergence of our algorithm. As you can see here, it's very light computationally and very effective in practice, given the high correlation between the parameters. So as you can imagine, the parameter space is very highly correlated because the statistics are generally very highly correlated. So edges and 2 stars, for example, edges is a statistic which is actually a subgraph of 2 stars. So the dependence between the statistics is very high, and so it is the correlation between the parameters. And the good thing about this approach, which is of course very computationally intensive, is that it's not affected by degeneracy issues. So this an important issue of these models, degeneracy, that can in practice make the life of standard, for example, MCMLE, Geyer-Thompson methods a little bit difficult because they're from MCMLE is generally very sensitive to the choice of the initial starting point, and this point is generally chosen as a pseudo-likelihood estimate. This pseudo-likelihood estimate can be, in some cases, can fall in some near degenerate or degenerate region, and in those cases, basically the convergence of the algorithm is not going to be happening, basically. So basically, in this case, we show that even if we start from very degenerate regions, so regions where the parameter value is only producing empty or completely dense graphs, we still have a convergence to the true posterior support, basically. So this is a nice property of this algorithm. So it's not affected by the degeneracy issue of in the sampling procedure. Of course, we are not going to solve the degeneracy issue of the model. So if the model is degenerate, we cannot solve the problem because it's a property of the likelihood itself. So we cannot solve the problem using a Bayesian approach in this case. Recently, we have tried to improve the exchange algorithm by proposing an adaptive approximate exchange algorithm with delayed rejection. So we adopt adaptive strategies, like, for example, based on Roberts and Rosenthal in 2007 and Harry and al. In 2001. So vertical adaptation. So we consider all the past parameter particles along the same chain. So we have multiple chains, as in the adaptive direction sampling. We want to use the information about past particles. We also have horizontal adaptation. So we tried different procedures, and they worked very well, even though the rectangular, of course, is the best one in terms of convergence, but of course it's the most computational intensive. So this is the algorithm. So we have a first stage move, which is exactly identical to the stage move that we have in the approximate exchange algorithm. But of course, instead of just rejecting and get back to the simulation of new data, we try a second move. So if theta prime, which has been proposed to the first stage, is rejected, we try a second stage move, and we to theta 2, and we accept or reject based on this probability ratio there. Acceptance probability, sorry. So this turns out to be particularly efficient. Of course, this, for the nature of this scheme, this didn't work very well with the adaptive direction sampling due to the nature of the adaptive direction sampling. But in, within adaptive strategies like these, the algorithm turned out to be very efficient. So we have a variance reduction of about 55% to 98%, according to our experiments, relative to the approximate exchange algorithm with adaptive direction sampling. Of course, the procedure is a little bit more computationally intensive because we instead of just rejecting, we may stay. We may propose a second move every time we reject. Of course, there are a lot of details that I'm not going to give you, in the sense that are, here the flexibility of implementing this algorithm is very high, so also we can think about proposing a very, reducing the variance of the second proposal, of the second move basically, or we can just sample a point theta 2 in the opposite direction with respect to the first stage move, and so on. Overall, according to our experiments, we have a better performance varying from 25% to 40%. So this has been a very important result. Of course, there are many other computational approaches in the literature. Doubly intractable distributions is a very important topic in statistics nowadays, and there are a lot of methods that have been proposed and that can be combined potentially in using also this scheme. So, for example, there have been proposed a generalization or further adaptation of the approximate exchange algorithm for ERGMs. All these procedures have been proposed are contained basically in this package BERGM, so Bayesian ERGM, which is on CRAN, so can be downloaded and used by practitioner. So basically, BERGM is the Bayesian equivalent of ERGM. So StatNet is one of the most important, most used suite of package for ERGM analysis. ERGM is the package for frequentist analysis, so it implements MLE parameter estimation. BERGM is actually implementing the Bayesian analysis. So we also have procedures for Bayesian model choice, which are based again on the approximate exchange algorithm. So we have generalization of the algorithm in order to sample from different models and perform model selection. There are also other methods for estimate the model evidence, and we have Bayesian goodness of fit procedures diagnostics. So this is just a very simple example of the package. So we have, for example, flow business, Florentine business network data, so very small data, 16 node data, where every node is a Florentine family, and the connection represent business links between these families. We want to use a very simple model, edges plus 2 stars. Here we have just to specify the number of iterations for the Bernini, auxiliary iterations, so the number of iterations used to sample at each step new auxiliary networks. Main iterations, 3000 is basically the number of the overall MCMC procedure. Gamma is equal to 1 is the parameter for the adaptive direction sampling algorithm. So the practitioner doesn't have to choose too many parameters to implement this. At least the ADS is very easy to implement. This is the output. Of course, there are also all the MCMC diagnostics. You can see the posterior distribution, the trace, and the autocorrelation plot. The results of the overall posterior density. So here we used 4 chains, actually. So these are the overall aggregated posterior density estimates. You can see the negative value for the theta parameter. Theta 2 is slightly positive. We used normal I just forgot to mention the priors. We used just normal priors for in this case. So in general, this is useful to have priors, and a Bayesian approach is very important because generally we know that networks are sparse. So we already know that, for example, the theta parameter is generally negative, and we can use a prior in order to support that information that we have. Also, generally, transitivity is positive in real social network examples, so we may want to include informative priors in our analysis. In this case, we just used very flat normal priors. Bayesian goodness of fit. So once we have estimated our posterior density, we sample 100, generally 100, but I mean the number can be modified. In this case, it's 50 actually. We sampled 50 parameter points from our posterior density. We simulate a network graph for any of these, for each of these parameter values, and we compare the realizations with our observed network. So these are the plots. So in this case, we choose this statistics, so the degree distribution, minimum geodesic distance, edgewise shear partners. This is a very simple model, so we didn't expect anything special in this case. So especially in terms of edgewise shear partners, the goodness of fit are not very good. Of course, we haven't taken into account transitivity in this case. So of course, transitivity in general is a feature to be taken into account. But this is just to give you an idea of the package, what it does. Okay, network dynamics. So an important issue in terms of important field of research is, of course, modeling network dynamics from an ERGM point of view. A lot of approaches, modeling approaches, have been proposed. So let's start from an example. So FDI relations. So for example, we have this network of foreign direct investments, relations between countries. So we are focusing on international electricity industry between 97 countries from 94 to 2003. These are the network structure that we are considering is binary. We focus on the change in the binary architecture underlying these FDI flows, basically. This is because so this is of course a very important simplification, recent results suggesting that the structure of international trade networks may be fully characterized in terms of their local topology properties alone. And as according to Squartini et al. In 2011, in order to properly understand the structure of the international trade system, it is essentially to reproduce its binary topology. So we focus on the binary topology for this reason, in order to compare the results to previous results in the literature. So we focus on the binary topology, even if these flows are, of course, weighted networks. So the research questions are: how did the current structure of the AI network come about, and what are the micromechanisms, so the network statistics in this case, driving its change over time? Do the local dependence effects change over time? And we also wanted to include a very well-known model, which is the gravity model. So the proposed by Anderson in 2011, the probability of observing a link between two countries is proportional to the product of their sizes, so in this case GDP, and inversely proportional to their geographic distance. So we wanted to include this information in our ERGM modeling framework. In terms of other network dynamics, in terms of ERGM modeling approach, have been proposed by Haneke et al. In 2010, temporal ERGMs. This approach is a discrete time dynamic ERGM in which the network at time t is a single draw from an ERGM conditional on the network observed at time t-1. Then this approach has been in some sense generalized by Kravinsky and Ancon in 2014. They proposed a separable temporal ERGM. So it's basically a generalization of temporal ERGM, where they basically have, instead of having just a unique process that that describes the evolution from t to t+1, they have two conditionally independent processes. So the formation process, consisting of the initial network with ties formed during the time step added, and the dissolution network consisting of the initial network with ties dissolved during the time step removed. So we have two processes that are conditionally independent given the initial network structure. Instead of using these approaches, we propose to use a different approach, which is a longitudinal ERGM approach. So basically we have, in this case, 10 observed networks. So we have a network observed at time t0 up to tm. And we generally, what we have is that we are assuming theta constant over time, and we want to inference to do inference conditional on the initial state. So given the initial state, we want to describe the dynamic process that has led to the final observation. So a first interesting question might be to also to include the information about, so to make inference also on the initial state. So we may want to include a model which describes the topology structure at the initial state, and then use a dynamic modeling framework to describe the evolution of this network over time up to the last observation. Furthermore, we may want also to relax the time homogeneity assumption by assuming that there is a parameter explaining the topological structure of the initial observation at time t0, and then we have different, for each time lag, basically we have a different parameter which is describing the evolution between two consecutive network realizations. So we decided to adopt a longitudinal ERGM approach. So we have an ERGM process consisting of a continuous time Markov chain which evolves through incremental changes that are basically toggles of ties with a certain rate rho. At each, we are assuming that there is a sort of continuous time evolution of the network, which is connecting basically all the consecutive network observations. So this is equivalent to a Gibbs sampler for ERGMs, and actually the limiting distribution is an ERGM. So this approach is actually very similar to the approach that has been used a lot in stochastic actor-oriented models proposed by Snyder et al. In 2000, in many papers. So basically, the conditional estimation is based on Bayesian data augmentation schemes. So basically, we suppose that there is a latent path connecting each consecutive network state. This path can be, of course, inferred. So our procedure of interest is the probability of theta given the latent path connecting, as I said, all the network realizations that we observed and the network realizations. So we have an augmented data likelihood consisting of our data set and latent paths, which are our augmented data, basically, which are augmenting our data, given theta and the initial state times a prior on the parameters theta. Estimation procedure can be, standard metropolis Hastings algorithm can be used in this case because the likelihood is tractable, basically. So this is the procedure to sample the latent paths connecting our observed network states. So every time the procedure is actually a little bit more sophisticated than the one you see there. There are a lot of details that I will not give you, but standard metropolis Hastings algorithm can be used in this case. The procedure is fairly computationally intensive. Okay. So initial conditions, we want to relax the conditioning on the first initial state. So generally we observe a set of consecutive network realizations, but we want to include also some information about the initial state. So how the first initial state formed, some information about that. So we assume that the initial state follows an ERGM with parameter theta minus 0, associated with the same effects that have been included in the longitudinal ERGM. So in this case, our target posterior is the probability of theta and theta minus 0, given the latent paths and the observed network states. So we have the augmented data likelihood, which is a longitudinal ERGM, times an ERGM, so these are independent, basically, times priors for both the parameters, theta and theta minus 0. So we are in this situation where we have a single parameter modeling the evolution of the network from the initial state up to the final state, and a parameter modeling the creation of the initial state. Estimation algorithm, we may sample the latent path as we showed using a standard MCMC procedure. For convenience, we treat the augmented data likelihood as observed, and then we neglect this step. So once we have fixed, we basically consider the augmented data likelihood as a normal likelihood. So we fix the sampled latent data, latent paths. And then we may sample theta and theta minus 0 from the posterior into blocks. So we may use standard MCMC procedures to sample theta, and we may use the approximate exchange algorithm to sample from the ERGM process generating the initial state. In step B, of course, the two parameters are treated as different parameters, but associated to the same network statistics. So we have the same set of network statistics. For example, we have included in our model edges, 2 stars, 3 stars, triangles, or generalizations of these statistics. These are treated, so these are the same statistics that we also include in our longitudinal ERGM process. But of course, in this case, the two processes are separated. So we want to relax the time homogeneity assumption. So we allow for the model to change piecewise, assuming different parameters for each interval. For convenience, we let theta change in discrete time, so the model is piecewise constant, but parameters are linked a priori through the process theta. So now we have process theta, which is basically linking all the theta parameters included in our model. So from the first theta minus 0 parameter, which is modeling the initial state, up to the m theta parameters that are modeling each learning process between two consecutive observations, network observations. So the structure of the model is this one here. So we have the initial ERGM for the initial, the ERGM process for the initial state x t0. Then we have a product of learns that are modeling the dynamic process between each consecutive network realization. And then we have a prior structure. So the distribution phi, which is so basically all the parameters are coupled through the process phi. So this is a very simplistic modeling structure, but it has the merit of basically improving the inference for this kind of models a lot compared to previous attempted analysis using the same type of approaches. So basically, in the estimation, we tried of course, the approximate exchange algorithm. We may use also some ABC methods. So standard, in this case, we adopted some standard approximate Bayesian computation algorithms. So we have the Gibbs update of theta. We generate new data from the learn process. For each parameter is generating a new realization. And then we accept or reject based on the distance, basically a distant measure between our simulated data and the observed one. And we accept or reject based on this distance and after fixing a tolerance value, basically a threshold epsilon. So we accept or reject with this probability. The scheme is conditional on theta minus 0, which is updated using the approximate exchange algorithm. So for the initial step, for the initial ERGM step, we still used the approximate exchange algorithm. This is a model specification that we used for modeling the FDI example. We have endogenous effects. So we model density, so the number of edges, reciprocity, number of mutual edges. Then we included some statistics that allow us to modeling the degree structure, in degree, out degree structures, transitivity structures. So we included alternating out stars, in stars, triangles, independent two paths. So these are effects that allow us to somehow describe the topological structure without taking into account any covariate information. Then we have the gravity effects. So homophily with GDP, so the number of links basically is a function of the GDP size of the countries, the sender effect, the receiver effect based on GDP, and then the distance between countries. The hierarchical structure of the model is the following. So we have the processes, all the parameters are basically coming from an independent normal distribution, and then we have the hyper-prior structure, so inverse Wishart distribution and standard normal model. These are the results. So we have the first graph on top left represents the rate of change between two consecutive network realizations. Then we have the estimate of mu, so of the parameter mu0, of the parameter mu. Yeah, here is the mean of the normal distribution. So the posterior distribution, basically, for the density mutuality, so for any of the effects that we have included in our model. So density mutuality of stars. The black lines represents the approximate exchange algorithm results. The yellow and red. No, I think it's green actually, but it displays that yellow. But the red and green curves represent the results that we got from the ABC method. So for different tolerance values. So the ABC is much less accurate in this respect. So a lot of work has to be done in order to improve the ABC, which is a little bit slightly less computationally intensive with respect to the approximate exchange algorithm, but of course it's less accurate in this case, and it takes a lot to. So we would need to specify a tolerance so small that basically our rejection acceptance rate is so low that convergence is very slow, basically. This is the posterior predictive distribution for each theta m per year. So yeah, from this box, it's not very easy to understand what's going on. So basically, the results are these. So there are considerable differences in rates of change over the period. There are effects for which it seems that the initial parameter is quite different from theta m. So the important thing is to notice that the initial effect, theta minus 0, which is basically modeling the initial state of the initial observation that we have, takes into account accumulated time heterogeneity of several years. So a lot of heterogeneity, a lot of topological structure is actually explained by the ERGM process, modeling the initial state. And then a lot of dependencies and a lot of structural effects have been are no more included, are no more explained in the dynamic ERGM process. Positive out-degree effect, possibly produced by a decline in cost and risk of entering a foreign market after the first entries. No evidence of transitivity effect. So this is important because generally in many social network applications, of course, transitivity is an effect that we observe. In this case, due to the nature of this type of graphs, transitivity is not important in describing the evolution and the formation of the initial state. So this modeling approach allows for estimating effects for the initial condition as well as the parametric form for the changing dynamics over time. The model approach used in this application, of course, is simplistic, but has the great benefit that improves inference considerably with respect to other approach that has been tried in the literature before. So the last part is just about network heterogeneity, which is another issue, important issue in the ERGM framework. So basically, the issue of the ERGM is that the underlying assumption is that across the network, the dependence structure is considered to be constant across the network. This is not reasonable. So if you observe a very quite big graph, assuming that there is a constant dependent structure across the network is not reasonable. There has been some modeling framework proposed by, for example, this is one, Schweinberger and Hancock in 2014. They proposed the hierarchical ERGM. The main purpose is to address model degeneracy, but of course they also take into account the assumption, but to do that they take into account the assumption that there is a local neighborhood structure. So nodes are basically belonging to different neighbors, and conditional on these neighbors ties within local neighborhoods are dependent, while ties between local neighborhoods are independent. So this is somehow relaxing the dependence structure, and it has the merit of also improving the properties of the model in terms of degeneracy. what we proposed recently is to include nodal random effects into ERGMs. So here we have a conditional interpretation. The logic of the probability of observing a link between two nodes, conditional on the rest. So with the rest of the structure fixed, is equal to theta times Sijx, as in a standard ERGM. But we also include some effects, phi I and phi j. So these parameters are actually explaining some heterogeneity due to the nodal effects in the network. In this case, the framework is quite general, so we may have any type of, so Ti and Tj are statistics based on the nodal, on the nodes, basically I and j. They may be also functions of some covariate information. We may also think about, instead of considering, in this case, we will focus on nodal random effects. So for example, we will consider the importance of the degree statistics based on each node. But in general, we may want to include random effects that are based on dyadic effects. So phi, the random effects, each phi I is IID from a normal distribution mu phi sigma squared phi. So the parameter mu phi captures the average propensity in the network to form an edge, so it's equivalent to the edge statistics, the parameter associated to the edge statistic. Therefore, the parameter associated with the edge statistics, theta 0, which is basically the baseline effect that we always include in the ERGM model, will be excluded from this model. So in this case, we will just consider Ti and Tj. The most naive statistic that we may consider is the degree distribution. So we want to include some information about the fitness of each node. So the importance of the fitness of each node in explaining the topological structure of the network. And we may also include some higher level statistics, like, for example, transitivity and cycles and stuff like that. So this is the structure of the model. We have hyperpriors, prior phi, theta. So we have fixed effect, theta I are fixed effect, and random effects, phi I. So this is the likelihood of the model. The posterior, again, can be written this way. Again, it's an double intractable posterior density. Pragmatically, we will estimate this. We may estimate this using, again, the exchange algorithm. Can be generalized very easily to deal with this posterior density. But we will also wanted to propose Bayesian model selection method. So we wanted to compare standard ERGMs and ERGM with nodal effects and compare them in order to understand when it is better to use standard ERGM, so with fixed effect, and a modeling framework with a mixed effect. So we have a standard ERGM. The model evidence may be written that way. So the probability of x given m1 is the likelihood times the prior divided by the posterior. In this case, theta 0 is the standard vector, including theta 0, which is the parameter associated to the density effect. In terms of ERGM with the random effects, nodal random effects, the model evidence can be written that way, and then we adopted basically the marginal likelihood f of x given the parameters is approximating using a Laplace approximation approach. So basically, the base factor can be written this way. This is the theoretical, how the base factor may be calculated. The base factor estimating using the posterior mean is estimating using the posterior mean values for theta, 0, mu, phi, and phi cap. For the variance of the distribution of the sigma squared phi, since the posterior is not symmetric, we plug in the mean of the log values and transform it back to, onto the scale of phi to sigma squared phi. The posterior density estimates are assuming asymptotic normality. So basically, we have that our estimation of base factor is based on this equation. So we have the Laplace approximation for the marginal likelihood there, and we also have to estimate that ratio of normalizing constants. So k theta 0 over k theta and sigma cap is a ratio normalized constant that is not available. To do that, to estimate that, we use a path sampling approach based on Gelman and Meng, proposed in 1998. That has also been used successfully in this ERGM context by myself and Niall Friel in 2013. And the important thing is that here the path sampling approach can be parallelized, so it's not too computationally intensive. So this is some results. So we used the Zachary network.
We might need to speed up a little bit.
Yeah.
Because we're supposed to finish quarter past, and we probably won't ask you a few questions.
Okay. Yeah. So these are the results. The posterior density. We used a very simple model. In this case, density and transitivity effect. The good thing about this approach is that we have now an explanation of the heterogeneity, but based on phi I. So the nodal effects, basically, as we can see that the most connected nodes, the most important nodes in the network are now explained by our model, and actually are explaining a lot of the topological structure of the network. The most important 3 nodes of the network are actually explaining a lot of also of the transitivity effects, actually. Okay, these are goodness of fit results. We compared the ERGM with nodal effects. We wanted to check whether our base factor approximation is good enough. So we wanted to simulate models from, so basically when we have base factor 0, we are basically fixing a model with add density plus 2 stars. We compare that model to the associated ERGM with random effects. We increased the value of theta 2 stars, so the parameter associated to the 2 stars, and as we can see here, the base factor is in favor of the standard ERGM. So when the 2 stars are distributed uniformly in the network, we tend to prefer to give more probability to the model, standard ERGM model. When the sigma squared phi, which is measuring the heterogeneity of the network, is increased, of course, our method is preferring the ERGM with the random nodal effects. So just to conclude, the modeling framework can be extended to allow nodal and potentially also dyadic specific network effects. So this is a very general, simplistic situation, the modeling framework that I proposed, but I mean, the framework can be generalized very easily and naturally. So all the results that we've showed in terms of base factor estimation and parameter estimation can be easily generalized for any type of modeling situation. We should know that the approach that we have introduced is, of course, computationally intensive because it's based on computationally intensive procedures. I just wanted to say that a promising avenue of research in addressing the issue of double intractable posterior distribution might be to explore methods based on composite likelihoods. So this venue of research is generally can be promising in the future. Okay, so this is it. If you have any questions,
yeah. Time dynamics that you proposed,
mm-hmm.
were they motivated by your data
example, or how did you come up with the time evolution mechanism?
The time evolution mechanism? No, I mean it's not necessarily motivated by the application. So the approach is a continuous time Markov chain. So we wanted to have a smooth transition, to model a smooth transition between two consecutive network realizations, instead of using like discrete time Markov chains. For example, term is just modeling the change. We wanted to include this approach that has already been very successful in other contexts, for example, in Siena models and stochastic actor-oriented models that are generally very popular in social science. So wanted to use the same type of approach. And there's a lot of literature about this type of approach. And so Johan Koskinen is actually one of the developer of this kind of dynamic approach. So yeah, it's been very successful, and it's very nice to have a sort of latent path connecting smoothly to consecutive. Of course, the price to pay is computational intensive. You always have this trade-off.
Sucks, right?
Yeah, exactly.
No, it doesn't.
Okay.
It was very nice, thank you. Can you do curved exponential families?
Yeah, potentially, yeah. You may want to include, yeah.
It's not in the package,
It's not in the package.
but you're pretty convinced that,
Yeah,
okay.
yeah, I'm still working on that, but yeah.
You are working on it?
Yeah, yeah.
Okay, good.
So we'll probably include that in the future realization of the package, yeah. Also in terms of static network, I mean, actually the longitudinal ERGMs are not currently implemented in the package, so only the static.
Okay.
Soon I will include the ERGMs with network effects.
But the static without.
The static
curve.
is going to be only static at the moment, and then we will be working on implementing At the moment, the code is quite fast, but has been implemented in MATLAB. So it's yeah. At the moment.
I have another question.
Yeah.
Want me to take it offline? Or?
Maybe because of scheduling problems.
Are you here the rest of the day?
Sorry?
Are you here the rest of the day?
Yeah, I will be here up to after lunch.
I have a question.
Okay.
Well, let's
Thank
thank the
you.
speaker again.
Thank you very much.